more than $700 billion. That is roughly what America's biggest technology companies are preparing to spend in a single year, building the infrastructure for artificial intelligence. Not on apps, on chips, data centers, power systems, cooling, and the machines required to run AI. The companies that already dominate the digital world are betting fortunes on one idea: whoever controls computing power may control the next era of technology. This astronomical sum belongs to a select group of tech giants: Alphabet, Amazon, Microsoft, Meta, and Oracle. In corporate finance, this spending is called capital expenditures, money spent on long-term physical assets designed to be used for years. While these highly profitable giants do not always report a clean AI-only line item, their combined 2026 capital expenditures are now expected to surpass $700 billion. This single-year budget is more than 3 times the total value of every major industrial megaproject breaking ground across America combined. The cash is rapidly turning into physical hardware on a massive scale. State-of-the-art processors, high-speed networking gear, massive memory stacks, storage systems, real estate, server campuses, and heavy-duty backup generators. Some companies choose to report these numbers as broad technical infrastructure, rather than separating AI-specific hardware from legacy systems. But the underlying tension remains. As the demand for artificial intelligence climbs, the physical bill is rising even faster, transforming what began as a software rivalry into the most capital-intensive industrial build-out in corporate history. The race for dominant technology has become a battle of physical mass. At the absolute center of this physical build-out stands a single company: Nvidia. Originally focused on video game graphics, Nvidia executed a massive pivot into artificial intelligence, turning its graphics processing units, GPUs, into the foundational hardware of the modern world. A GPU is a massively parallel processor designed to run millions of mathematical calculations simultaneously, making it perfectly suited to train and serve complex AI models. But manufacturing these processors requires a highly concentrated global supply chain. Nvidia designs the silicon architecture, but physical fabrication relies almost entirely on Taiwan's semiconductor manufacturing company, TSMC. From there, the silicon wafers undergo advanced packaging, a specialized process that bonds the processors with high-bandwidth memory, which is fast memory that helps AI chips move data quickly. Finally, specialized networking gear links these systems together, allowing thousands of distinct GPUs to coordinate as a single supercomputer. This specialized pipeline means the AI boom is creating large winners far beyond the software companies building chatbots. Equipment suppliers, silicon foundries, packaging specialists, and memory manufacturers are capturing billions of dollars in revenue. Computing capacity itself has become the ultimate strategic resource. More chips translate directly to faster training, quicker experimentation, and broader deployment. In a global race where software algorithms can be replicated, the true barrier to entry is not the code, but the physical ownership of advanced compute. The physical reality of artificial intelligence is found in giant concrete warehouses packed with thousands of humming servers. This shift turns a software competition into a massive construction and energy challenge. Tech companies are racing to buy land specifically positioned near high-voltage transmission lines and power plants. Some planned server campuses require as much electricity as entire mid-sized cities. To secure this massive volume of power, companies rely on power purchase agreements, which are long-term contracts to buy power at a set price. Through these agreements, hyperscalers are locking up output from nuclear reactors, natural gas plants, and renewable wind and solar farms. Yet, Buying the chips and signing the energy contracts is only the first step. The physical power grid cannot keep pace with the demand. High-capacity transformers, the critical grid equipment used to change electrical voltage so it can travel safely across transmission lines, are in short supply, with delivery times stretching for years. Administrative hurdles also block progress. Delays in government permitting, grid interconnection backlogs, turbine manufacturing shortages, and the need for specialized liquid cooling systems to prevent servers from overheating are stalling projects across the country. This creates a stark imbalance. A company can spend billions of dollars to purchase the most advanced processors, but those processors are useless without the physical infrastructure required to plug them in. To understand the financial tension, look at free cash flow, the actual money a business has left over after covering its day-to-day operating costs and funding major capital investments. In the second quarter of 2026, Alphabet reported a negative free cash flow of $5.9 billion, the first such deficit in its history as a public company. Yet, during the exact same earnings announcement, management raised its capital spending plan for the year to a massive range of $195 billion to $205 billion. These tech giants remain enormously profitable, backed by strong core businesses that generate billions of dollars every month. The issue is not insolvency, but rather the stark mismatch between immediate costs and delayed returns. Independent analysts project that if current spending trends persist, the combined capital expenditures of these tech giants could actually surpass their total free cash flow by 2027. To justify these outlays, the companies are banking on several distinct revenue channels. They are renting high-performance computing power to developers, charging subscriptions for autonomous AI assistants, and using machine learning to boost the efficiency of their core advertising and internal operations. Even without standalone paid products, AI can add silent value inside existing businesses by streamlining workflows. But the physical bills are due today, while the massive financial payoffs may still be years away. The central unresolved question is how much new money must flow into the AI ecosystem, and how quickly to justify the most expensive infrastructure build-out in corporate history. This massive spending mirrors the late 1990s internet boom, when telecom carriers poured more than $500 billion into laying 80 million miles of fiber optic cable. When that cycle ended, nearly 85% of the network lay unused, driving massive corporations into bankruptcy. Billions in market value vanished as prominent operators collapsed. Yet, that identical dormant network ultimately became the physical foundation for high-speed internet, streaming services, and the cloud. Speculative excess and durable physical assets routinely coexist in the same cycle. The critical question for this current era avoids the simple binary of bubble versus revolution. Instead, it focuses on which specific layers of the hardware stack will end up overbuilt and stranded, and which will survive to form the permanent infrastructure of the next global economy. The infrastructure race is expanding from a corporate clash into a geopolitical contest. While the United States uses export controls to restrict China's access to advanced silicon, Chinese engineers are finding workarounds. Labs like Moonshot AI and DeepSeek are building highly capable systems, including the Kimi K3 model, by focusing on algorithmic efficiency rather than raw hardware volume. This effort relies on China's massive manufacturing scale, deep electronic supply chains, and vast power grids. If Chinese labs can achieve comparable results with far less compute power, the financial logic of the massive Western hardware build-out shifts overnight. This rivalry extends far beyond a single chatbot. The true contest is for control of the entire computing stack, spanning semiconductors, physical facilities, electricity, software models, cloud platforms, talent, and supply chains. History warns that the largest builder does not automatically capture the value. IBM pioneered the personal computer architecture, yet lost control of the hardware standard to competitors who commercialize clones. In this build-out, the ultimate advantage may belong to those who build the largest systems, or those who achieve identical performance at a fraction of the cost. Ownership of the computing future remains unresolved. $700 billion can build an extraordinary amount of computing power. It cannot guarantee that customers will pay enough to justify it. The AI race is no longer only about who can build the smartest machine. It is about who can secure the chips, electricity, infrastructure, talent, and money required to keep those machines running, and who can turn all of that investment into something the world is willing to pay for. The next technological empire is being built right now. We just don't know who will own it. Every empire leaves a paper trail.